In this video, we'll look at an intro to the Keto-Enol tautomerization. So we've seen this once before when we looked at the reaction or the hydration of an alkyne. It makes an enol, which then tautomerizes to a keto. So we're going to look at it again and look at some chemistry of the enolate ion, which is formed under basic conditions. So if we look at the possibilities here, we have this guy right here, which is an enol, and that is in equilibrium with what we call the keto form, where I have a double bond to the oxygen, and then the H is over here. So what we're seeing is the transfer, the migration of one group. In this case, the group is an H. This guy is called the keto form because it resembles a ketone. Could be an aldehyde as well. And these are in equilibrium with one another. Generally speaking, the equilibrium lies towards the keto and away from the enol. So in most cases, the keto is the more stable tautomer. And that's because the carbon-oxygen double bond is stronger, and so it favors thermodynamically that tautomer. So if we look at an example here, I'm going to use an aldehyde so we can see. So this position, the carbon next door to the carbonyl carbon is the alpha position. This is the beta position, and this would be the gamma position. So H's coming off the alpha carbon are going to be acidic. So they have a pKa in about the 16 to 20 range. For reference, water has a pKa of 15.7. So it's not super acidic, but it's acidic enough that it can be removed, especially if you have a strong base in solution. So any proton, let me change colors here so we can draw that guy on, coming off of this alpha position is going to be an acidic proton and one that we can remove with a base. So we can influence the acidity of that proton at the alpha position by introducing different groups. So for example, if we took these two examples here, this chlorine is electronegative. It's pulling electron density away via induction, and it's weakening the bond. And that makes it more acidic. So it's got a smaller pKa. So this is more acidic. The pKa of this top guy, acetone, is 19.3, and the pKa of this chlorinated acetone is 14.1. So one thing that can influence the acidity is the introduction of an electronegative atom, and this would be via induction. So having an electronegative atom on that alpha carbon makes that proton more acidic by pulling electron density away from it. Resonance has a similar effect. So again, acetone has a pKa of 19.3, and if we put a benzene ring there, so we're talking about this H here, this pKa is 15.9. So this is more acidic, and that's because it has resonance structures. Now, that said, it's still going to be negatively charged carbon wherever it goes. So the resonance definitely makes it more acidic, but it doesn't have quite the impact we might expect because of the negative charge being circulated on a very not electronegative atom in carbon. So if we look at this situation where we have two carbonyls on the same structure and they're going to be one apart from one another, this pKa is equal to 9. Those are very acidic because there's resonance structures where the negative charge is going to be on the more electronegative atom, which is the oxygen. So in this case, I could put in solution a base like OH minus, and I could pluck that proton off. And first we'll just put those electrons onto the carbon atom. And there I have a negative charge. And then these electrons can swing up and kick that up, giving me a negative charge on the oxygen atom. And this species with its resonance structures is called an enolate ion because it's charged. So an enol is neutral, an enolate ion is charged. We can take a lone pair on this oxygen, kick that down, kick these over, and kick that up because it's able to be resonance stabilized on that side as well. And that gives us this guy. So there's a lot of resonance involved in this enolate ion, and you have that charge shared on pretty electronegative atoms, and so that's going to make that acidity even greater. So that's an easier proton to pull off. So in solution, when you have a strong base like OH, you're going to have some enolate ion present in solution, okay? But if I want to convert completely or nearly completely to enolate ion, I'm going to need a stronger base. So as an example of that, if I think, I'm going to put this starting material here, got the H coming off of that alpha carbon. There's no H's on the other alpha carbon. So if oxygen with a negative charge is a strong base, then nitrogen with a negative charge is going to be an even stronger base because it has, it's less electronegative and it's small, so it'll be less stable with that charge. So I'm going to use this guy, okay, and this is called LDA because it generally comes as a salt, so it's lithium diisopropylamine. And the reason that you have these isopropyl groups here is because they're bulky. And so then we can keep this thing from acting as a nucleophile. It will only act as a base. So this is the equivalent of our bulky base, which we've seen before with like tert-butoxide. So this guy can come in. Let me change my color here. We'll use red. And it can deprotonate this. And then I have these resonance structures. Go over here. Go back to blue. And then that resonance structure. O minus, there. So in this case, actually, what it looks like, because of this strong base, is the equilibrium lies in that direction, towards the enolate ion. So if I want to use, if I want to get a large number of enolate ions in solution, I need to use a stronger base. I use a bulky base in this case so that I can avoid having it act like a nucleophile and attack the carbonyl carbon. So that bulky base is a strong base, and it converts almost completely to enolate ion.